Now that we've talked about the planets, let's start talking about their moons and ring systems. So starting with Jupiter, Jupiter has 4 of the largest moons in our solar system. So altogether there are 7 large moons. There's our moon, 4 of the moons of Jupiter, 1 around Saturn, and then another one around Neptune. We'll talk about those in a bit. So these 4 large moons are referred to as the Galilean satellites. Can you guess why? So these were discovered by Galileo. When he first, he didn't invent the telescope. When he first made his telescope and looked up in the heavens, he saw these 4 moons going back and forth from side to side of Jupiter. So from closest to Jupiter to farthest away, these are Io, Europa, Ganymede, and Callisto. So Io is the closest, and Callisto is the farthest. So here's our first clicker question of today. Which of Jupiter's moons will orbit the fastest? A. Io, B. Europa, C. Ganymede, or D. Callisto? Think about it and we'll discuss in just a bit. Alright, so this goes back to Kepler's laws, and Kepler's laws state that the farther away a planet is from the sun, the slower it orbits. The same thing actually applies to moons around planets. So, the one that goes the very fastest should be the one that is the closest, and that is A, Io. Io is the fastest. So all 4 of these moons orbit in the same direction and in nearly the same plane, which is above Jupiter's equator. So the moons also orbit in the same direction that Jupiter rotates. So all of this is showing us evidence of conservation of angular momentum. Now, as we look at them from the Earth, we see their orbits nearly edge on. There's a slight tilt, but we do see them nearly edge on. So from our point of view, we see them go from one side of Jupiter to the other side and back. They seem to swing back and forth from one side to the other. Io has an orbital period of 1.8 days. So what this means is that every 1.8 days it has orbited completely around Jupiter. This is fast enough we can actually see it travel in a single night. Callista has an orbital period of 16.7 days, so that's long enough we don't really notice it in a single night, but if we track it for a couple of nights, then it becomes obvious. From edge to edge, the entire moon system, at least the 4 Galilean moons, spans around 15 arc minutes, which is about half the width of the full moon. Also, each of the 4 Galilean moons are actually bright enough that they could be seen by the naked eye. Except we have Jupiter that's right in the middle of them, and if you remember, Jupiter is one of the brightest things in the sky, which means the moons get washed out. We're just not able to see them. However, with simple binoculars or a simple telescope, you can actually see the 4 Galilean moons. Now, each of the Galilean moons is in synchronous rotation. So think back, what does synchronous rotation mean? So this means that one orbit and one rotation take the same amount of time. So this also means they always keep one side facing towards Jupiter. Not only do we have all of them with synchronous rotation, but Io, Europa, and Ganymede also have what we call an orbital resonance. And orbital resonance means that they keep lining up in the exact same place in their orbits. Their orbital periods are even integers of each other. So in this case, for every time that Ganymede has gone around exactly 1 time, Europa has gone around exactly 2 times, and Io has gone around exactly 4 times. So because of that, they always line up in the exact same place in their orbit, which actually leads to some interesting gravitational effects, which we'll see in a little bit. Europa is the smallest of them, and it's actually a bit smaller than our moon. Then is Io, then Callista, and then Ganymede. Ganymede is the largest of the Galilean moons and is actually larger than Mercury. Based off of spacecraft orbiting, we've been able to determine the densities of each of the Galilean moons. Io and Europa have densities similar to the crust of the Earth or the density of our moon, so that suggests that they're probably made of rock and metal. Ganymede and Callisto have smaller, lower densities, closer to around 2,000 kilograms per meter cubed. This suggests that they do have some rock and metal, but they probably also have a large component of ices. Now, we believe that Jupiter had enough mass as it was forming to actually produce its own proto-moon disk. So just like the Sun formed the protoplanetary disk and we had the planets forming there, Jupiter was large enough to form a proto-moon disk, and the moons formed around Jupiter in the same way that the planets formed around the Sun. We also see this kind of difference in composition. So close to the Sun, we have the terrestrial planets because that region was hot and ices weren't able to form. Then farther out, we get the Jovian planets because we were able to form ices, which means the planets got big enough to trap in a lot of gas. Around Jupiter, close in would have been hot, and we get moons that are made of rock and metal, Io and Europa. Farther out, it was cold, similar to the outer solar system, so we not only get rock and metal, but we also get ices, and we see that Ganymede and Callisto are made of rock, ice, and metals.